Morning, everyone. My name is Michael Mann, and my project was on modeling error and measurement in GKP states. I'm going to be the first of a series of talks from our quantum computing group, so I'll hopefully get you from the basics to where my work is in a short amount of time. So we're going to start with, we do quantum error correction, so we're going to start with what error correction is very briefly. And then we're going to go into harmonic oscillators, our specific architecture, and what GKP codes are, and then different ways of measuring and constructing them. And then finally, we're going to compare the different methods, followed by a little conclusion. So what is error correction? And we're going to talk about a lot of different ways to encode information. But as a brief little example or a metaphor, let's say we're coding things into our chessboard with our chess pieces here. These are all rooks. If you bump the chessboard, it's really hard to tell which ones had an error, especially if they moved completely to the space next to them. And if they do have an error, what space they started on, so it's hard to correct. But let's say we started with all bishops and we started all our bishops on white spaces. Now, if you have an error, you've got a much easier job telling which ones have an error because they're going to be on a black space, and you're far more likely to be able to predict which space it originally started on. So a good error correction code has a few components. First, you can't use all the spaces. You need to divide your space into a logical subspace and an error subspace. And that will increase the likelihood that your error is both detectable and correctable. And secondly, you want the error correction scheme to match the type of error you have. So for example, if we were hitting the board on the corner here and your pieces were more likely to move diagonally, this would be a bad error correction scheme because you'd be more likely to go from a white space to a white space. But when we hit the sides, we've got a pretty good error correction scheme. Now, the only difference between this is when you're working with quantum computers, you can't measure any of the states, otherwise they will collapse. So things get a little more tricky with quantum error correction. And so this is our quantum computer. This entire little module is going to be on a gigantic freezer running at absolute zero. But what you need to know that it has two parts. First is our transmon. It's a qubit. It's a two-level system, which means it can be a 0 or a 1, or all the superpositions in between, with this being more likely to be 0, more likely to be 1. It's also nonlinear. This makes it really good at measurement and readout and allows us to apply our computational gates. We also have the microwave cavity, which is an infinite level system, which means it can hold a lot of information, but it is linear, so we can't do all the different gates. But that's really good because it has a high dimensional space at error correction. And we know from our great engineers that our primary method of error will be photon loss. So we can narrow what our errors to be to one dominant error type. This is described by a harmonic oscillator, which is any system that is going to oscillate, exchanging position and momentum. A classical harmonic oscillator can be completely described by its initial state because we will know how it will oscillate. But with quantum harmonic oscillators, there are a lot more varieties of different ways you can do with superpositions, opposition momentum, and negative probabilities like these directly. So you can do this with a cat code, a binomial code, but specifically we'll be using the GKP code to create a relationship between our qubit and our harmonic oscillator. And so the way you do that is specifically, you want to make the 0 state of your qubit correspond with this state right here, where your particle is very likely to be measured in a position of either 0 or plus 2 pi, plus 4 pi, every interval of plus 2 pi. And your 1 state is in between them. So it still has a spacing of 2 square root pi, but it is shifted, so it doesn't overlap. And the reason we do this is because one of the reasons we do this is we have this great control displacement gate, which allows you to map, if you measure the qubit and it measures as a 0, you're much more like, you're saying that you are in this state. And if you measure it as 1, you're saying you're in that state. But obviously we can't use that for error correction because we measure our qubits. They're no longer in a superposition of 0 and 1. So we also have this stabilizer gate, which can ask just, are you on any of the units of pi or square root pi? So that allows you to say, are you in either the 0 and the 1 space? Are you in that logical space? And the back action, if you're not in the 0 or 1 space, if you had an error, it will collapse you back into the 0 and 1 space if you set up your stabilizer right. So the only difference between that ideal theoretical case and the thing in our lab is that we can't create infinitely precise peaks. We have to deal with wave functions. And so they are going to have this finite energy envelope and a width that we call delta. And we can vary this width delta based on our optimal parameters. And we can also adjust our measurement operator and our stabilizing operator for the delta we have in our system. So this is just get a little bit into what our stabilizer does. We want it to work so that if you are in the logical space, it returns it to the exact same state. But if you are in the error subspace, it moves you down from photon loss back into your original subspace. And here is our model doing exactly that. We start with a 0, we have a photon loss, we run our SBS algorithm, and we are back at the 0 state. And if we have no error case, we can run the exact same program, and hopefully it will, or statistically, it will return you back just to the exact same state with no changes. So there are 2 ways to construct our GKP code. Let's say, and we're doing all this in Python through a module called Qtip. The first way is using a formula, which this formula looks very complicated, but we can break it down where this is a squeezing operator, which is varying you by width delta. This is your displacement operator, which is reliant on n, this infinite sum, where you're saying that you will have a displacement at every wide unit. And to create an area underneath that curve that is not infinite, we've got this beautiful Gaussian envelope, which is defined by this operator right here. Now, there's another way you could build this, and it's a little more realistic to what they actually do in experiments, where you take your finite energy stabilization and you run that over and over again, and then you ask what states are invariant. And using those states as eigenvectors of this operator, we can build an orthogonal basis, a 0 and 1 state basis, and we construct our 0 and 1 states around that basis. So just a little review. We've got 2 different ways to measure our GKP states. First, we've got the traditional ideal one, and second, we have this finite energy one, which accounts for delta. And we have 2 different ways to formulate our GKP states. One is using our classic formula, and second is using this more complicated procedure where we take the SPS operator and we build it using the eigenvectors. So we want to compare, or I wanted to compare, how these different ways of preparing states match up and perform with different measurements. So on our left here, we've got measurement infidelity, and it's log scale. So if you are lower, that means you are doing much better in your measurements. And if you're higher, it means you have a higher infidelity, you're more likely to measure it wrong. So let's just look at these straight lines here for a sec, where we have under ideal measurement conditions, when we're not adjusting for delta, we see that our SBS prepared state performs very slightly better than that formula state. But if we measure using that finite energy protocol that does account for delta, we see that our SBS state is doing a lot worse than our finite measurement, or our ideal formula state. And this is really surprising because the SBS is built in a very similar way from our measurement, and you would assume that this red line here would be better because they're using very similar operators that are built out of kind of a similar toolkit. And then we also have some interesting data when we get into the error case. So what we're doing is just zooming into this top part so we can see it a little more clearly, where we can see that the dotted line here, or the dashed line, is what happens in photon loss and what happens with photon gain. So all these do worse. If you have an error, you're less likely to measure it correctly than if not. But we can see that our system in these models does a lot better when you have photon loss, and a lot worse if you have a photon gain operation. So that's another interesting thing that we found out, and it's good considering our dominant area is photon loss. But we can also compare within these different kind of subgroups where we still see that the finite energy SBS is outperforming the ideal formula prepared state, but if you in the photon loss condition or photon gain, but if you switch to photon loss, then you're actually having a better outcome with the finite measurement and SPS together. So there's some interesting nuances and differences between these two. So yeah, so it opens us up to further questions and future directions. So one is our state prep from the SPS operators are worse under the finite edge range measurement and better under the ideal measurement. Why? Why is that true? We're not really sure. Second would be, is there a way to better optimize for that SPS state prep? If it's not the finite measurement the way that we thought it would be, would it, is there a different way to construct it? Is our code working the way it should? Whenever you get surprising results, you want to check everything, which we have, but it would be worth trying to replicate it. And you can use this also code base to ask different questions about the system, like how would it perform under repeated redoubt? All right, thank you.
Any questions?
Mind going back to the first result that you showed,
Yes.
can you comment on why the finite energy curves,
Mhm.
I'm looking at the solid lines,
Yep.
why would it have this lower measurement infidelity than ideal curves?
Yeah, so our finite measurement curves, oh, because in the ideal, so when we look at our state prep or so with our ideal curves, there is this some part of our delta function that deviates by delta from the ideal case where you are exactly on each of the peaks. And so what your finite energy measurement is doing is accounting for that. And so it basically shifts your delta while you're measuring. So that does a little bit better because these parts of the Gaussian peak that are slightly off get corrected for or accounted for in the measurement in a way that the ideal would literally just be asking on delta or not.
Okay,
Because the ideal is built off of that like theoretical space where your delta is 0 and your peaks are infinitely tall.
okay, thank you.
Anything else?